All right, so this question here is going to take us a few minutes. First to interpret, and then there's several steps to the solution. So we've been given some positions on a coordinate grid system. So let's start by just sketching out what that would look like. And this handy graph paper here. So we have several objects, and it tells us that the objects are placed so that M1 is at the origin. Okay, so here is my mass number 1. Right, let's label that M1. And mass 2, we can see, is at the coordinates 0, 2, which is going to put that object about here. It's also a larger object than the first one, so I'll just draw it a little bit bigger. And clearly this distance here must be 2, seeing as it is at that coordinate point. So that there is 2 meters. And then finally, the third object, this 4.8 kilogram mass, is at the coordinate 4, 0. So, where would that be? Well, 1, 2, 3, 4. It's going to be right here. And it is the biggest object yet. I forgot to label M2 over here. And this one will be M3. Distance-wise, well, this distance here clearly has to be 4 meters. So that's the positioning. We do not know the gap, the diagonal gap between M2 and M3. We could find it if we should happen to need it. But what we're being asked to find is the resultant gravitational force on the object at the origin. So, in other words, we need to know the combination of the 2 forces on this object here at the origin. So there's going to be 2, right? There's going to be one force upwards. Let me change color on those arrows. There's going to be one force upwards. Let's go with a green one. Because of M2, right? So there'll be a force upwards there. We'll label that in a second. And then there will be a force in this direction due to M3. Hard to say which one should be bigger at this point because M2 is smaller than M3, but M2 is closer than M3. So let's see. I've got to call these something. So I'm going to call this one the force on mass 1. So that's F subscript 1 because of mass 2. So it's F subscript 1, 2. That's quite a common way of delineating those different forces. So using the same notation, this would become the force on 1 because of 3. Right? So F1, 3. Okay. Now clearly once we found those 2, we're going to have a vector addition to do that's going to involve some trigonometry. And if you are not great at the trigonometry, then just follow the steps I do and solve it that way. And don't worry too much about it. Just focus on understanding of the gravity at this point. Okay. So Well, there's two forces we need to find, right? F12 and F13. So for any gravitational force, we know that the formula is big G m1 m2 over r squared. So for mass 1 and mass 2, that's going to be 6.67 times 10 to the negative 11. That's the value of big G, always is. Times mass 1, and mass 1 is 1.9. Times mass 2, and mass 2 is 3 kilograms. All divided by the separation squared, and the separation is 2, so 2 squared. Alright, let me just work that one out. And that comes to 9.5 times 10 to the negative 11 newtons. It's a pretty tiny force. But then, you put some masses on a pool table a couple of meters apart, and you wouldn't really expect there to be very much gravitational force. Alright, let's find F1, 3. So F1, 3. It's going to be big G, M1, M3 over R squared. I should have called these R's different things, shouldn't I? Otherwise, it can get confused. Let's call that one R1 and that one R2. So R2 equals 4 meters. R1 equals 2 meters. All right. So 6.67 times 10 to the negative 11 times mass 1 is still 1.9. Mass 3 is 4.8. So 4.8 all divided by, and the distance this time is 4 meters, so that's 4 squared. And that equals 3.8 times 10 to the negative 11 newtons. So in terms of the battle of the two masses, which one has the bigger effect? It's going to be mass 2. Its force is several times bigger. So what do we do with those? Well, let's draw a little vector diagram. F12 was in this direction here, and F13 was in this direction here. Smaller, so put it there. So when you want to add two vectors together, remember that the answer is always what you get when you draw your two vectors nose to tail and draw a line that goes from the very beginning to the very end. Just move that a little closer to the perpendicular. And we can do that, and when we do that, we will find that the answer is always equal to the same as we would get if we just did the diagonal of this triangle here. Oh, my tablet's being a little bit slow right now. That'll do. So, like I was saying, if we were to just take these two vectors and draw them nose to tail, come on. So let me just show you what I mean. Duplicate that one, put them over here. Take the second one and put it nose to tail. Oops, sorry, I didn't mean to actually move it. I want to duplicate it, so duplicate it. Put it over here, nose to tail with the first one. Well, the answer to a vector addition is always the line you get when you go from the very beginning to the very end. So what we're trying to do is find the length of that red line and then later on the angle of it. Now, quite obviously, we know that this one here is going to be hang on, sorry, what is it? 9.5 times 10 to the negative 11. So that's 9.5 times 10 to the minus 11 newtons. And then the other one, should have labeled them, apologies, that's F1, 2. This is F1, 3. So F12 was 9.5, and then F13 is 3.8 times 10 to the negative 11. So if we know the length of those two sides, how do we find this missing one here? This is, actually, let's not call it R because that will confuse things. R is usually used in vectors for the resultant, but let's call this F net. So how do we find the net force acting on that? Well, it's a right angle triangle. We all know how to do this. So the net force is going to be the square root of the sum of the squares. So 3 times 10, sorry, 3.8 times 10 to the negative 11 squared. Be careful with your calculators. Make sure you're in scientific notation. 9.5 times 10 to the negative 11 squared, and we will take the square root of all of that, and that works out to be 1.02 times 10 to the negative 10 newtons. So the net force acting on this object is 1.02 times 10 to the negative 2 newtons. Now we need to find the angle. Let's just look back to the question and see which angle we're being asked to find. Well, it says above the x-axis. So the x-axis is here. Oops, pull an arrow. This is the direction of the x-axis. And if that is the x-axis, then above the x-axis means that angle there. So you can find the interior angle of the triangle, subtract it from 90 if you want to do it that way. Clearly, by the law of the giant letter Z, that and that angle must be the same. So let's just solve for theta. Given that this is a right triangle, this side here would be the opposite side, and this side here would be the adjacent side. So opposite and adjacent, well, that's tan. So, oops. So we can write that tan theta is opposite over adjacent, which in this case, opposite is that one. So 9.5 times 10 to the negative 11, and the adjacent is that one, so 3.8 times 10 to the negative 11. So theta must be the inverse tangent of that number. And that works out to be 68.2 degrees. All right, that's it. Should we see if we're right? Let's do that. So 1.02 times 10 to the negative 10. 1.02 e minus 10. And what did we say? 68.2. 68.2. Yay. All right.